much as so this is a great opportunity for me to also connect with students in physics. All right, so I'm going to give you a really broad talk about what we do in geophysics and in particular what we do in our group at the University of Ottawa. Here's a QR code. If you want to look at our website, I'll put it up again in my last slide. So first, let's talk briefly about my career trajectory. How do you actually become a geophysicist? Well, for me, it started with an undergraduate degree in physics at the Université de Montréal that I got in 2003. And it's really during this undergrad degree that I decided I wanted to pursue geophysics as a career. In the first year, after my first year of study, I did an internship in medical physics. Didn't really turn out well for me. It didn't like it too much. And then I was trying to look for another field that I could apply my physics skills. And then looked into geophysics. At the time, there was no geophysics taught in the physics degree. So I did my own research and found a supervisor actually at UQAM in Montreal who did geophysics, and I did an internship there. And then the year later, I did a year abroad in Switzerland where I took many courses in geophysics and geology to get up to speed for a master's degree. And then I continued into a master's degree in earth sciences, not in physics, because there's no geophysics in the physics department. So geophysics is typically hosted in earth sciences departments. So I did this at UQAM, got my master's in 2005, doing modeling of gravitational acceleration on the Earth. And then after that, I wanted to do seismology, which at the time was done mostly at UBC. And then I did a PhD in geophysics at UBC in 2008, then did a postdoc at Berkeley, and ended up as a faculty at the University of Ottawa since 2011, still hosted in an earth science department, and therefore that's why I don't get to don't get to connect with physics students too much. So, what is geophysics? You're not taught this in the physics program, probably because geophysics is an applied physics, and it's a branch of science that studies Earth using principles of physics and involves measuring, analyzing the Earth's physical properties, gravitational field, magnetic field, electrical, and seismic characteristics to understand structure, composition, and processes, and to monitor how these things can change with time and what this is telling us about the evolution of our planet. And also other planets. We can do planetary geophysics on Mars, on the Moon, on Venus, for example. So in essence, geophysics explores what's beneath the Earth's surface or other planets' surface and within its interior using physics-based quantitative methods. Just a few pictures showing you the kind of things that we look at. So for example, how the internal structure in the Earth is composed and how it's actually dynamically changing inside the Earth that's giving rise to plate tectonics and earthquakes and how we record those earthquakes. And that's going to be the general theme of my presentation. And before going into the seminar, I just wanted to briefly show you the kinds of things that we do in our group. I've tried to illustrate this with a Venn diagram with the outermost green circle encapsulating the overall objective that we do in our group, essentially studying earthquakes, tectonics, and natural seismic hazards. And we're going to use New Zealand as a natural laboratory through this seminar to show you the kinds of questions that we're interested in, mostly about tectonics, earthquakes, even volcanology in New Zealand. To do this, we need data, and we go out and collect our own data, which can be either on a boat, on a cruise. Here is an example of taking an ocean bottom seismometer, putting it on the ocean floor, taking it back on the ship, and then getting our data this way. And bottom picture is me installing a seismograph station in the Yukon, for instance. So we do field work. There's not much lab work in geophysics. There's some groups that do like rock physics, for example. They crush rocks and they see what happens. But we do field work and computer work. And there, of course, everything is rooted in data science, data analysis, as well as numerical modeling. We develop our own computer codes. We publish them openly with all documentation. So that's the kind of things that we do in our group. So a very brief introduction. Now let's go into content of today's talk. And again, it's going to be a very high level. I'm not going to go into too many details, and hopefully you'll learn something new. I put this together thinking about what I would have wanted to hear as a undergrad in physics at the time. So there's divided like into several themes: tectonics, earthquakes, and tsunamis, which are like the motivation for doing what we do. A little bit about seismic wave propagation in the Earth, very high level. And then discovery of recently of slow earthquakes, which are not typically felt on the surface, and they're called episodic slow earthquakes. I'm going to tell you a bit what they are, why we are interested in learning about them. And then recording waves underwater, that the experiment we're currently doing in New Zealand. The ELVS acronym stands for Earthquakes and Locking Investigations of Subduction. And then with these ocean bottom instruments, we can actually capture a lot of dynamics that's going on in the ocean with seismic waves that we wouldn't be able to do otherwise. So we're using seismic data to understand things that are going on in the ocean, in addition to listening to earthquakes and all the rest. So I'll start with a map. I don't know if you're like me. I love to stare at maps and look at all the tiny details. If you turn on Google Maps and the terrain layer, this, and you Google New Zealand, this is what you'll get. And essentially, you see essentially two main islands, a couple of smaller islands. The main islands are creatively called South Island and North Island. I'm going to use New Zealand as an example because I've spent a great deal of time in Wellington recently, and show you the kinds of things that we can see from these maps, and then going into more detail. So if you just look at the terrain map, this is what you'll see. Nothing much interesting. Obviously, there's mountains on this side and a little bit of topography, but not much you can tell from just looking at this map. If you turn on the bathymetry, now you start to see something popping up in the background. And this is actually the outline of shallow waters. What's in light blue here is essentially shallow water in the middle of the ocean. So let's say less than 300 meters deep, where everything is kind of lighter blue. And this here is even 100 meters deep. So this is telling us something, right? New Zealand is part of something greater. It's just the submerged part of that actual underwater continent called Zealandia. And here's another map. This is the same data. It's bathymetry, and essentially the topography on the seafloor, as well as the land bathymetry. And the colors are false, of course, with warm colors indicating shallow waters. And now you can see these really large landmass here that is really under shallow water. You see many other things as well, like this trench arc pair. It's essentially really, really deep ocean floor, like 6-7 kilometers deep, and paired with a volcanic arc. And you see these chains going up in all of these regions with the trench. There's one here to the north of New Zealand. There's one here to the south. And now if you look at another map, this is a geological map. Okay, I'm not going to give you any detail. It's telling you the different compositions that we observe on land and also at sea if we do some extrapolation. So I want you to focus, for example, on this red band here, and you see that it should be fairly continuous. And when it gets to New Zealand, it turns and then comes back here to the south. This is really indicating this should be linear, but it's highly curved because there's a large fault on the South Island of New Zealand that is essentially shearing up apart this whole continent. And you also see the volcanoes up here and in pink color. So you get more information and you start to incorporate more data in these maps. And here's another one that's a geophysical data. This is gravity anomalies in milligauss. This is another unit for meters per second square. And now here you see a deep blue is a deficit in acceleration, gravitational acceleration, meaning there's a mass deficit in this region, essentially because it's really deep waters. And then you have a mass excess right next to it, and that's the volcanic chain that's built up next to it. So this is telling us New Zealand sits in the middle of something here on both sides, and we know now there's this giant fault that's shearing it apart. So New Zealand is actually a very tectonically active region that is being sheared apart by what we call subduction zones. And this is, again, framed in the paradigm of plate tectonics, where the Earth is split up into a mosaic of small to large tectonic plates. The largest one is actually the Pacific plate here. And if we just look at northern New Zealand here, this is a cross section of, let's say, about here. And this is where the Pacific plate subducts or dives under the Australian plate. And it does it like all along the Tonga Carmatic Trench here. This is called a trench. And it goes all the way to the tip of the North Island. Then it becomes the Alpine Fault. And then it also happens to the south as well. So we are interested in these subduction zones because this is where the largest earthquakes can be generated on the planet. So another map, again, this is showing bathymetry, but now with a bit more detail, showing the faults. And you see now the main fault, the plate boundary fault that separates two plates, is shown in this black line. And here you see the subduction zone in the North Island, then the Alpine Fault, and then another subduction zone that's going the other way. So New Zealand is truly being sheared apart. But something interesting here in the northern part of New Zealand, which is shown here, is that in the north, closer to the deep ocean trench, we have differences in the seismogenic potential of the fault. This means different parts of the fault can generate smaller or bigger earthquakes. In the north here, this is a cross section, for example, A prime here. So in the middle of the North Island right here, we see that on the plate interface, this is where big earthquakes are generated. It's actually not generating or storing elastic energy towards a big earthquake. It's slowly slipping, and it's something I'll come back to later. And then deeper is called a steady creeping zone. So essentially there's nothing happening. It's just slowly flowing rocks next to each other. But if you go a little bit further south, actually closer to Wellington, excuse me, you have a part of the fault that's stuck. And it means that when it's trying to go down, the friction in the fault is high enough to keep it together, but the forces are still continuing to deform this area. And eventually this is going to be released in a really big, what we call mega thrust earthquake. So understanding the links here between, let's say, the seismic structure, the bathymetry, the faults, with this kind of lateral change in coupling or earthquake potential is one of the driving questions that we have. Why is this important? I was just telling you about these slow or creeping zone versus regions that just generate normal earthquakes. We call those fast earthquakes or slow earthquakes. And this is just showing around the Pacific where these slow earthquakes happen. There's some even in Canada, the US, Mexico. And also on these stars are the world's top 10 mega earthquakes ever recorded. And they're also sitting near the boundary of these regions. And New Zealand is here. And historically, there hasn't been a big earthquake in New Zealand, but we know they happened in the past before settlements. So this is likely a region where big earthquakes can happen. And this is all interesting and important because these megathrust earthquakes can generate tsunami waves. So how does a tsunami occur? Recall that we have these really large faults on the seafloor, and when there's a motion on these faults creating an earthquake, you also have vertical motion along the fault. These faults are dipping, and therefore, when they release energy, things go up and down. So this displaces a lot of water in the water column, and this sets off oscillations that develop underwater at great speed. The speed of a tsunami wave is about 800 kilometers per hour. That's like the speed of a jet plane. So it can take several hours to cross the Pacific, but it's still pretty fast. And then the sea gets sucked under on the shore because you need to conserve volume and mass. And then when that wave arrives, it goes up the slope and then it generates these really large tsunami waves. It's not a normal wave with a crest and it's just an incoming wall of water that just doesn't stop. This is an example of what happened in the last really big tsunami earthquake, this magnitude 9.1 Tohoku earthquake in Japan. You see this ship sitting in a neighborhood, and you see the picture of the tsunami front hitting the coastline. So that's one key reason why we need to understand and study these subduction zone earthquakes. You probably heard of a recent one that occurred a couple of weeks ago, July 29, and magnitude 8.8 Kamchatka earthquake and a tsunami generated a tsunami in the Pacific. Fortunately, not as damaging as the Japanese earthquake. The epicenter is here in Kamchatka. This is the island of Kamchatka. Japan is here. And here you see all the magnitude 8 earthquakes and above along this subduction zone. This is a really long subduction zone, and it keeps rupturing in different places at different times. For example, the 8.8 ruptured here first, right next to a magnitude 9 earthquake that happened 75 years ago, almost. And this is the tsunami wave that was generated by this Kamchatka earthquake. This is in meters. Yeah, so it didn't reach really high waves for an earthquake of that size, thankfully. But you see that along the Hawaiian chain, as soon as you hit some kind of land, then you get increases in wave heights and the damaging tsunami, even all along the coast in North America, South America. Okay, so what happens during these earthquakes? And I'm going to show you, this is not a simulation, it's actually the recording of this earthquake from a bunch of seismometers. And these are primarily located here in North America, although we can do this kind of analysis with most of the seismograph stations deployed on the surface. There's way more than these, but these are just the ones that were used for this earthquake. And so I'm going to take you through this animation. And this is a seismogram from this earthquake. The light gray is the unfiltered data. The dark black, well, the black line is the filtered. We're going to look at this seismogram from this station here from an earthquake that started here. And you're going to see colors. Blue is the ground going down. Red is the ground going up. And you're going to see also some bars, some tick bars that are showing the horizontal motion, horizontal component of motion when an earthquake like this sends seismic waves. So when, for example, the red bar is going to move to the right and hit these wave arrivals, P wave, S wave, Rayleigh wave, relative to this station here. So you're going to see the waves propagating through the network and arriving here. So let's do this. This is the earthquake. You see the P wave that's coming in here. Now it arrives at this station here. This is the fastest wave and really small amplitude. And now behind it, you see the S wave, already much larger amplitude. It's already here. And then you have the surface waves, those really high amplitude damaging seismic waves. And you see the horizontal motion with these bars. So this is a pure visualization of seismic waves propagating on the Earth. And even this earthquake generated like what are called normal modes, essentially the Earth ringing like a bell for several days or weeks. And this is picked up by these instruments. So one thing we can do when we have a large network of instruments like this is essentially back project all the energy to the source and look at how the rupture happened through time on the fault. And so this is another animation. This is again the island of Kamchatka. And now we're using all of these seismograph stations and in a kind of beam forming towards the source to try to track how the earthquake itself was rupturing during that time. And so these are the end results, but I'm going to show you an animation of how rupture happens in a fault like this. So remember, this is a big subduction zone. This is the epicenter. And we're going to look at how energy is formed on the surface of this fault. So it starts here. That's where the epicenter is located. Then you're going to see it move on one side, and then it goes to the other side. It moves up and down as well, all the way to the trench, and then it jumps to another region. And this is showing us that earthquakes are not these really continuously, slowly propagating rupture fronts of a single fault. They jump in different places. And that's something we learned in the recent decade for these really big earthquakes. Of course, a small earthquake is not going to do anything like this, but for the really big earthquakes, they take their time propagating and they're not continuous. They jump in different places. And that's because there's different properties of the rocks in these regions that give rise to this behavior. So a little bit of sort of seismic wave 101. Maybe you know this already, but if you solve the wave equation in a homogeneous, purely elastic medium, you get these different types of waves. Body waves, P waves, and S waves. Body waves are waves traveling through the entire volume inside the Earth. And P waves are compressional waves. Essentially, they compress and dilate in the same direction as the propagation, as the wave propagation direction. And shear waves travel perpendicular to the direction of propagation. But these are both body waves. P wave is first, S wave is second. And then you can also generate these surface waves. And these are caused by essentially waves that are trapped and constructively interfere near the surface of the Earth. These don't go through the whole volume. They stay near the surface because seismic wave velocities are smaller. It acting like a waveguide for these bigger waves. And you see love waves have a polarization. So the motion on the ground is completely tangential to the propagation direction. And Rayleigh waves have an sort of anti-clockwise rotation relative to the propagation direction. These two waves are damaging ones. And going back to this animation here, now you'll see P wave going fast, arriving first, low amplitude. S wave is somewhat greater amplitude. This is actually a reflection of an S wave. And now you're going to see the love wave actually traveling faster and the Rayleigh wave arriving afterwards. So again, P wave is here, the wave front, and it propagates across this network. Now the S wave is here. It will arrive to the station a little bit later. And now you see the generation of these surface waves up here. And now they'll arrive at the station. You see the love wave. Now, this is the love wave generating this kind of motion. Behind it is the Rayleigh wave. You'll see it better towards the East Coast here. You see these bars kind of rotating, showing us the Rayleigh wave. So really, these waves do exist and propagate inside the Earth, but you see a lot of heterogeneity in these recordings. It's not like a uniform wavefront that propagates away from the source. There's all kinds of small differences in the way these waves propagate. Part of it is due to the source, as we just saw, and another part of it is due to the structure of the Earth, essentially because the Earth is not homogeneous, and we can use these recordings to learn about the interior of the Earth. So the Earth is layered, heterogeneous, and we know this from seismic waves that propagate across the globe. And for example, we know there's a liquid outer core because P waves get refracted back towards the center of the Earth when they hit this interface, and therefore there's no P wave that can be recorded here. And we know it's liquid because there's no shear waves propagating in this layer as well. So we see these, we get these discontinuity structure in the mantle. That's the part of the Earth that's the greatest volume in the Earth. And then when you hit the outer core, the S wave drops to zero. P wave drops as well, but not to zero. And then when you get to the inner core, the S wave picks up again, meaning the inner core is solid and not liquid. And so you can look at really fine structures in these layers, how they change with time, as well as what's their thickness, composition, things like that. And you can also do imaging, isn't it very similar to medical imaging in the sense that you have a bunch of sources, which are earthquakes on scattered on the earth, and you have a bunch of receivers, the seismograph stations. And with travel time anomalies and things like that, you can reconstruct the 3D volume inside the earth and see things like downgoing subducting plate all the way down to the bottom of the mantle. Sometimes these blue structures here, blue meaning faster than average seismic velocities, and they are related to subduction because subducting plate are oceanic plate. They're cold, they're from the surface, and then when they go inside the earth, they warm up, but they remain cold all the way down, and therefore we can track them with seismic waves. I'm not going to go into too much more detail here. I wanted to go back to New Zealand and give you the questions that we're interested in, again, with all this framework of subduction zone earthquakes in mind. Again, we go back to the North Island with this detailed map. And we saw that in the North Island, we have this slow slip zone. And then right underneath it is the steady creeping zone where pressures and temperatures are too high to essentially generate fractures. And it's just flowing very slowly. But in the southern part of the subduction zone, we have the stuck plane interface. And that's the region that we're interested in. And I'm going to give you another really brief lecture on an earthquake cycle, something very intuitive and simple, is how we understood the earthquake cycle, let's say 40, 50 years ago. This is a conceptual model based on a block slider model. For example, you have a block sitting on a surface. It has a mass and therefore a normal force applied to this surface, a normal stress, and it acts like as a clamp and wants to keep the block from moving. And then a spring with the elastic constant, that's the elasticity of the earth. So the fault would be the surface here, and the spring represents the elasticity of the earth. And as you're essentially trying to pull on this block, the earth deforms elastically, and eventually you pull and you continue pulling, and the stresses on that surface will be overcome and the block will slide. So this is represented in this stress versus time diagram, with stress increasing linearly with time. Then you reach the strength of the system, essentially determined by the friction of this surface. And then there's an instant drop in stress because this block moves, and then it goes back to a background pre-earthquake level. And this cycle then resumes with time. There's a linear increase in stress and then a drop. So with this model, stress changes linearly with time. Threshold is reached at peak strength and fault rupture occurs. Then the stress drop is constant, meaning the magnitude of the earthquake can be determined. And in this really simple model, earthquakes are completely predictable. In reality, things are more like this, where the threshold for the strength of the fault changes with time. It's not linear or constant. The stresses vary non-linearly with time because there's a lot of things happening in the crust all the time, and therefore it's unlikely that things will just be simply linear. And the stress drop also changes with time. It's not necessarily equal every time. It can go to a smaller value, it can go to a lower stress level, and therefore there's nothing predictable about this model. There's other reasons why this earthquake cycle model actually fails. For example, the thickness of the fault changes, the properties along the fault change, the rheological parameters of the fault change. So many things occur together to make this simple model actually impractical. But we found that some parts of subduction zones may actually be completely predictable, contradicting this model. So this is a map of Western Canada, Vancouver Island. Vancouver is around here, and Victoria is here. And there's also a subduction zone in Western Canada, and they have a bunch of what are called GPS stations. They're like GPS, like you have in your car, but they're ultra precise, and they record their position on a sub-daily uh, measurement. And here you see the north and east component of motion for a station in Victoria. And what you see here is on the long term, this station is moving to the northeast. And that's what this black arrow is showing here for Victoria. But then something happened in the year 1999. You see this station actually reversing its motion towards the south and towards the west. And this was captured here. There you see the red arrow is capturing this reverse motion. And normally this is an indication that an earthquake happened, a big earthquake that would have been felt to move the ground this way. But there was nothing recorded. So people were puzzled. You can actually estimate the magnitude of the earthquake that should have happened there to create such a motion on the surface. And it turns out to be equivalent to magnitude 6.5 or 7, which you should definitely feel. And it can create damage as well. But there's nothing felt, nothing irregular here. But they still looked at their seismograms really carefully. And what they found is this kind of really incoherent, like propagating noise wavefront with many noise signals or bursts. For comparison, an earthquake would last seconds, maybe minutes, and these things last for minutes to 30 minutes, hours, days, even in weeks. And this is telling us that there's something going on the fault at the same time as we have this displacement on the surface. And because there was no earthquake recorded, they called this a silent earthquake. But it's silent because it occurs over a 2-week period. It's a big earthquake, but it's moving so slowly that we don't actually feel it. And when you continue to monitor this motion, you see that on average, yeah, the station is still moving to the northeast, still showing signs that a big earthquake will happen. But superimposed on this, you see this pattern of increasing and then drop, increasing, drop. And every time it drops, there's an increase in these seismic bursts. They're called tremors. And the wonderful property of these slow earthquakes, they have another name, also called episodic tremor and slip, is that they actually are periodic. For example, here in the northern part of the subduction zone in Canada, it's about 14 months. So we can predict really precisely when the next one is going to occur. But it also changes along the coast here, where there's this subduction zone. So 14, 15 months in the north, 21 months in the middle, and 10 months in the south. And the energy in these events is also varies along the coast. And therefore, there's obviously something that's controlling this behavior and can tell us something about the really big earthquakes that are threatening. And this also occurs in New Zealand. And I was telling you before, we have this region of slow slip, so slow earthquakes. And they're shown here by these contours and in red. And there's another one here. These bigger contours in red are where these events occur. And you see that we still see this lateral change in behavior, whereas in the northern part of the island, these events occur near the trench, way offshore, and there's not much going on land here. There's a really tiny one that occurred here. And there are other big ones that occur, but now in the south, they're much further inland, they're much bigger, and they have a different recurrence time as well. So These signals are not as nice as the ones we had in Western Canada. They don't show this really nice periodicity. They're more chaotic, but they show the same behavior. So here we're kind of reversed because motion on this fault would produce motion towards the ocean, so towards the southeast. But nevertheless, so you see that in the south here for station TAKP, maybe it's hard to see, but you see these really long inter slow slip episodes and then really long slow slip and then it enter slow slip and then a slow slip episodes. So different durations, different periodicity, different recurrence, and therefore there's something fundamental that we like to understand here. And that's why now I'm going to tell you a little bit about our current project. That's why we decided to go out and install seismometers on the seafloor in this part of New Zealand where the plates are supposed to be stuck together and generate and then store elastic energy towards the next big earthquake. And this contour, this orange line, is where this locking boundary occurs, where you have deep slow slip further down on this subduction zone, shallow slow slip in the north, and then it bends. And this part is where it's locked and accumulating stress towards a magnitude 8.5 to 9 earthquake. And we installed seismic stations here to listen to the ground to tell us, is there any earthquake activity in this region? So that's the crew, the scientific crew. That's what these instruments look like. This is our setup to communicate with these instruments once we get contact with them. And they're left on the seafloor for a full year. We don't talk to them, we don't touch them. And then we go back a year later, pick them up. This is one floating in the water as we were picking it up. And then we have a year's worth of data to analyze and try to figure out what's going on. And here's the boat that we were using, the RV Tangaroa. Here's a picture of my PhD student, Taylor. And here's the deck crew handling one of these seismic instruments. That's actually a video, which I'll show for you. There's sound, but it's not really helpful. This is the crew that's doing this part. None of the scientific crew gets to touch these instruments as they are going overboard or picked up because it's very sensitive, and the crew is the experts who do this. But I was on that boat and think this is it's fair weather, but we were in pretty rough waters sometimes. So the fun of doing field work, actually. And just a little bit more about this project. We're going to use ocean bottom seismic data with AI earthquake detectors. AI has been used a lot in picking actually the onset of P waves and S waves from really tiny earthquakes that occur all the time in New Zealand. And it increases the detections tenfold relative to an earthquake that's detected by an array, but reviewed by an analyst. So this is these stations, the network of seismic stations in New Zealand. They're all on land, unfortunately. And so all of these earthquakes that occur offshore are not really super reliable. And there's probably a lot of them that are missing because they're too far away from the network of stations to be picked up. And then we decided to put our stations here. This is a previous experiment called the Pulse experiment, and our station are those. We don't have data. We don't have earthquakes picked yet. We just recovered these in February and haven't had time to work on these data. But a previous deployment using offshore ocean bottom instruments, the Pulse network, was used. And you see the before and after detections for these earthquakes. So we expect something like this that can be picked up by our network. So we are going to be able to see where are the structures, the stresses building up towards the next earthquake on both sides of this ocean trench in relation with the locking on the plate interface. So when you put a seismometer on the ocean floor, you don't just listen for earthquakes. You pick up anything that's going on in the ocean. And one of those things that we are going to be looking at is actually trying to track whales around New Zealand. That's been shown to be possible with ocean bottom sensors. And so for example, whales gave off, they sing, and therefore this is the spectrogram of their song essentially. And you could probably say this is an individual or this is an individual, and you can then match them. This is probably the same individual, or maybe they're talking to each other, and you can track them with individual animals or as a group. You can locate them using seismic methods as they move and migrate up the coast or anywhere. So that's one thing we're going to be looking at, trying to find biosignatures, signatures of wildlife in the ocean using seismic instruments on the seafloor. Another thing we can do when you have an instrument on the seafloor is look for things that move on the seafloor. And one of those are turbidity currents. They're essentially big landslides that occur underwater. We rarely hear about them, but they can actually generate tsunamis as well. And they occur along big channels. This is the Congo River in Western Africa. And here they installed ocean bottom sensors in the channel to try to record these really large mass wasting events on the seafloor and understand their dynamics, if they lose energy or not, and where they deposit, is that controlled by structure or anything else. So that's one thing we'll be looking at as well. Another thing we can do is actually do meteorology with instruments on the seafloor. You can track storms if they're going over your network of instruments, of course. And this is a spectrogram of energy for one of these stations, showing how energy is building up as a function of frequency in the water column and how this propagates along the network. So you can look at this. You can even look at ice calving events when big chunks of ice on like polar ice caps detach. You can pick that up with seismometers as well and do seismology with glaciers and all other a lot more signals that you can pick up. Another application is, for example, to detect ships. The various navies in the world don't really like this, but you could detect any ship going on the surface by the noise they make and the vibrations they create on the ocean floor and tracking them. And you see, these are again spectrograms showing everything that's going on in the ocean. Some of them are earthquakes. These are ships. These are bottom currents, and whales are at different frequencies. The blue whales in one set of frequencies, fin whales and pygmy blue whales. So there's a lot of things happening in the ocean. It can be picked up by seismic sensors, and that's what we're going to be looking at as well, in addition to earthquakes, to study subduction zone structure. So this is actually the end of my talk. And in conclusion, just to reiterate what geophysics really is and what we do, geophysics combines fieldwork with data analysis and physics modeling to understand and monitor our planet. That's the underlying theme when doing geophysics. Of course, I've shown you examples in seismology, but there's a lot of different physics-based fields in geophysics. And at the University of Ottawa, our group is involved in geophysical problems to image and monitor subduction zone earthquake processes using seismic data recorded on the seafloor, as well as all of these additional signals that we'll try to understand and use to understand and monitor our planet. And if you want to learn more, you can check out our website, uogeophysics.com, or this is the QR code for it. And or email me if you're an undergrad student and never heard about geophysics and want to know more, or are looking for a master's project or anything. Spread the word. If anybody's interested, I'll be happy to talk to them. And that's my group in the recent past. And yeah, that's it. I'll stop here and take questions.